So here we are driving on the road in the sunny Pacific Northwest because it rains, so we worry about these things. It's not sunny. That would be a lie. Although today it is, so we'll be happy for that. So here's my car going around the corner. This is the tangential velocity is this 14 meters per second. It should have units in there. And then the radius for this curve is this 50 meters. So let's see. What is my free body diagram? Hopefully you've done that. So pause this and do it if you haven't. Okay, let's take a look. Let's take a look. So I'm going to look at it kind of from the side view, like I'm looking at it on the ground. So here it is on the ground going around the corner. So my force of gravity would be kind of coming straight down. My force normal would be straight up. And then the center of the circle then points this away. So I have some force making me turn. So these are fun because we're kind of used to those at this point in time. So here's force gravity, here's the force normal. It's not the rotor ride, so it is indeed just straight up perpendicular from the surface. Then I have this center seeking force. With the center seeking force, the only one that's left is friction. So this must be the force of friction. I want to remind myself I'm accelerating towards the center in the same direction as friction. So I'm going to go ahead and call to the right and up as positive. Cool. So now I can do a summation of forces. So summation of forces for my center, which is also my x, is going to be my force of friction equals my mass times my center seeking acceleration, mv squared over r. And my sum of forces in the y, let's see, up is positive, so force normal minus down, force of gravity equals, we're not flying up in the air and we're not plummeting down to the bowels of the earth, so this equals 0. And I remind myself that I needed this because, let's see, we are in motion. So in motion, I should do this in a different color, reminding me that the force of friction equals the force normal times mu. So I needed to define the normal. So from my sum in the y, I get the force normal equals mg from the force due to gravity. So then the force of friction equals, let's see, force normal times mu. So here's the normal, mg, times mu. Just made that substitution there. So now I look at this, well, the force of friction is the thing that's making me go in the circle, so I've now defined it. So I have mg mu equals mv squared over r. Now, of course, I started doing these things just out of sheer habit without even considering how much of this, if any, I needed. So after I cross out my m's, because I'm like, oh, hey, look, that's always happy. I get to cross something out. Now I can look to see. Will the car make it if it's going this 14 meters per second? So I have a couple of options here. I can look at this as its max coefficient of friction and use this to solve for the max velocity. Any velocity above this coefficient of friction, so in other words, something that is opposing the motion, because remember, this force of friction is the thing making us accelerating. So if I solve for a velocity that is greater than the value I determine here, then that says that it can't handle the force of friction. I'm sorry, it can't handle the velocity that I'm actually going. So I can do that. The other option is to take the velocity that I have, plug it in, solve for mu, and compare my mu values. Whichever way makes you the most comfortable, you can go with. My preference is just to solve for the max mu given this coefficient of friction. So let's see, I'm going to have, or max v, sorry. So I'm going to have radius times gravity times mu, being the one here, equals v squared. So if I take the square root of this, then I get the velocity, the max velocity that I can make this turn. So I have 50 meters times 9.8 times this 0.60. Boom, there's my v. So it turns out, I feel like I kind of chose the kind of slower or faster path. Doesn't always happen. 9.8 times 0.6 to the 1/2. And that says that the max, V max then is 17.146 meters per second, which means that I will stay on the road at that 14 meters per second and all is good. So let's think about this again. My tangential velocity, that is the piece that I can use for my center seeking acceleration. The radius of this corner is that 50 meters. I'm trying to go around that corner and stay on the road. To do that, I need to not make the force of friction unhappy, because that is the thing making me go in the circle. So that's if you've ever felt like you're getting ready to go too fast, lose control going around a corner, that's because you've overcome the force of friction's ability to keep you turning. So I went that route. These substitutions here, because it's in motion, I can make that substitution. That the force of friction then is defined in terms of the normal. From my summation of forces, I define the normal here in terms of gravity. So I had this, make sure that looks like a G. So the force normal equals mg. From that sum, the force of friction in terms of the normal, then mg is the normal times mu. So I make that substitution. And then I can come back up here. I have the force of friction defined as mg mu. And I can put that in and solve. So it should make us happy, because by the time we get here, the one thing that stayed consistent is that when these were the only forces involved, the masses canceled out, so I didn't need it. And then I had two routes I could go down here. I could solve for the max velocity for that coefficient of friction, or I could have used the velocity I was going to see if it was going to be a larger or smaller coefficient of friction than the one that I have. It's whatever one makes the most sense to you.